Here's another very difficult function to compute, near prime of n. We'll say that this function is either equal to 1 or 2. It's 1 if there is a prime p between 100 to the 100 to the n, which is a big number, and 100 to the 100 to the n plus 10 to the 10. Okay, so this is a few million. So we're looking for whether there's, in the next few million numbers past n, whether there's a prime. Now usually for small n, there's almost going to be certainly a prime in that interval, which contains a few million numbers. But when we go further out into the numbers, the primes get thinner and thinner, then it's going to become the case that such a phenomenon is rarer and rarer. But unfortunately, it's enormously difficult for us to compute any kind of situation like this when we're talking about numbers which are so big. Okay? So although we can sort of effectively, theoretically talk about this, practically it's almost impossible to get a hold on this kind of rule. Here's a function called Riemann of n, which is 1 if the Riemann hypothesis is true and 10 say otherwise. The Riemann hypothesis is a famous unsolved problem in mathematics. We don't need to worry about what it is. Let's just say that a lot of people are working on it, they'd like to solve it, but they don't know whether it's true or false. Most people believe it's true. The question is, does this define a proper function? And if not, let's say in 2 years from now, if someone comes along and proves or claims to prove a Riemann hypothesis, does it suddenly make this function a valid function? And then if 10 years later someone finds a crack in that proof, what happens to the nature of the function? It's a question. So our list of which functions are going to be accepted as legitimate rules or legitimate procedures is getting a little bit more nebulous. We're approaching the boundaries of where this idea really should stop and start. But saying where that boundary is much harder. Let's look at some more examples. Are we going to allow functions from natural numbers to natural numbers that depend on physical quantities, that depend on the world around us? For example, offspring of n, the number of people alive today with n children. That depends on the world in which we live in. We have to go around counting things. The number of people like this is going to be very hard to count, almost impossible in a practical way. Or how about ox atoms n, the number of atoms in n water molecules. Okay. So a water molecule, H2O, has 3 atoms in it, so you might say, well, the answer is simply 3n. But what happens when n is so big that there are surely no amount of water molecules in the universe of that size? Does this function still make sense? It's a philosophical question to me, and it's like, does one hear the sound of one hand clapping? Can one talk about n water molecules if the n is so big that it's impossible for there to be that many water molecules in the universe? I don't know. And here's a function, ask norm of n. With this function, if you want to know what ask norm of 7 is, you have to ask me, and I'll tell you. Okay? So it's whatever Norman J. Wahlberger says it is. So you want to know what ask norm of 7 is? I'll tell you it's 19. And I'll also tell you that ask norm of 314 is also 19. And ask norm of 1 is also 19. But that's all I'm going to tell you now. If you want to know more about this function, you just send me an email and I'll tell you more about it. Okay. Are we going to accept that as a function? Well, I think most of us would probably say no. But maybe some of you might think that this is quite a legitimate function. Here's a function related to a famous unsolved problem. Let's call it 3,2 of n. There's a famous problem that says if you start with the number n and you do the following procedure, if it's odd, you replace it with 3n plus 1. And if it's even, you divide by 2. So if we start with 5, for example, 5 is odd, so you multiply by 3 and add 1, you get 16. And then you divide by 2, 8, 4, 2, 1. And then you get 1, and then after that it cycles 1, 4, 2, 1, 4, 2. And people conjecture that no matter what n you start with, it will always end up finally, after a long, long cycle perhaps, in this cycle 1, 4, 2, 1, 4, 2. So let's say that the function 3,2 of n is 1 if this cycle with input n eventually goes to 1, 4, 2. And otherwise, it's 2. So again, nobody knows whether this function is always 1. Probably is equal to the constant function 1, but we don't know. And it's very hard for us to compute for very, very large n what this is likely to be. Now you can kind of see that this is sort of a random selection. I could easily make up dozens more curious conundrums. Is this a function? Is this not? Is this rule acceptable? Is it not? Does this procedure really make any sense or not? I'm sure you can also make up lots of questions like this. So here's the problem. The problem with a function definition is that it's not containing bounds on what we mean by an acceptable rule or procedure. Without a very clear boundary of where the definition stops, it just doesn't really make sense. So this is a problem that you don't need a PhD to understand. I think you can all appreciate what the difficulty is. And unfortunately, it's very hard to surmount this difficulty. Next time, I'll tell you what I think the right way of thinking about functions is. I hope you'll join me for that. I'm Norman Wildbacher. Thanks for listening.